Okay, in this section will be this video will be the kind of the second part of section 2.2. We're going to go through the derivations of the derivative of the sine and the cosine, and then we'll finish up the video with an application of a free-falling object. So the claim here is the derivative of the sine is cosine, and so we're going to use the limit definition of derivative. However, we'll use h instead of delta x. So this is going to be the limit as h goes to 0 of sine of x plus h minus the sine of x all over h. And so we're going to go back to a sum of angle formula, which is the sine of a plus b will be equal to the sine of a, sine of b, cosine of b, and then plus the sine of b and then the cosine of a. So you would have seen this in either pre-cal or trig course. And so we're going to go ahead and apply that to the first part of the quotient there. And so that'll be the sine of x cosine of h plus the sine of h and then the cosine of x minus the sine of x all over h. And what we're going to do is a little bit of trickery because we're kind of stuck here, but we're going to use our special limit. So the limit as h goes to 0 of the sine of x, well, if we're doing that, it should be h over h is equal to 0. And we'll also be, it's not 0, it's 1. The other one is 0. The limit as h goes to 0 of 1 minus cosine of h over h. That one's going to be 0. So we're going to use these two special limits here, but we gotta extract it out of this. So what we're going to take a look at is we're going to grab this and this, and we're going to factor out a minus 1, and that's going to give us this part here, the 1 minus cosine all over h. So we're going to grab that. So that's going to be the limit as h goes to 0. We'll grab those two, factor out a negative sign, and we'll have 1 minus cosine of h all over h, plus, and we'll pull out the cosine of x, and we'll have the sine of h over h. And those are our two special limits, so we have the negative sine of x times 0, and then the cosine of x times 1. Now, remind you that the h is the only thing that's moving, so the sine of x and the cosine of x, they're constant in this limit. So we don't have to worry about them moving. And out pops the cosine of x, and that is our derivative, and that's something that we'll need for the rest of calculus and differential equations and higher math. So you'll need to know that derivative of sine is cosine. We'll go ahead and do a quick derivation of the derivative of cosine, which is going to be minus sine, and we'll use another sum angle formula. So this will be negative sine of x. So limit if h goes to 0 of the cosine of x plus h minus the cosine of x all over h. And this time we'll use the sum formula. Cosine of a plus b will be equal to the cosine of a, the cosine of b, minus the sine of a, the sine of b. And again, you would have gotten this in pre-cal or trig. So we're going to go ahead and rewrite that as cosine of x, cosine of h, minus sine of x, sine of h, minus the cosine of x all over h. And we're going to employ the same trick we did before. We're going to try to get a special limit, the 1 minus cosine x over x, or in this case h, and then a sine of h over h. So we're going to grab this and this, and we're going to factor out a minus cosine this time. So instead of a minus sine, we'll factor out a minus cosine. So limit as h goes to 0. So we'll grab those two, minus cosine x comes out, and then we have 1 minus the cosine of h all over h, plus, well, we'll say minus, and pull out a minus sine of x. And there we got our two special limits. So it'll be minus cosine of x times 0, and then minus sine of x times 1, and that'll be the sine of minus sine of x. Okay, and we'll do two applications of this. One thing I'll mention is I kind of think of it as like maybe a ladder. So here's sine, derivative of sine is cosine, derivative of cosine is minus sine, Derivative minus sine will be minus cosine. Derivative of minus cosine will be minus sine, or just sine. Derivative of sine will be cosine. Derivative of cosine would be minus sine. Derivative of minus sine will be minus cosine x, and it's just going to repeat itself. So if I want to do derivatives, I'm going to follow the ladder this way. Later on we'll think of something, or we'll learn something called an antiderivative, and that'll actually allow us to go upwards. But for now it's just the derivative. So we're going to do an application here. Because we're doing trig, we're going to have to know some stuff about the unit circle. So that'd be something that you want to study. So we'll do two examples. Find all values for which f prime of x is equal to 0 in the interval 0 to 2 pi. And we'll start off pretty basic. We'll look at the sine of x. Okay. So we're looking at when the derivative is equal to 0. Well, we just learned that the derivative of sine is cosine. So f prime of x is going to be equal to cosine of x. And so we're looking at solving cosine of x is equal to 0. That happens at the north and the south poles, so that'll be pi over 2 and 3 pi over 2 on your unit circle. We'll do a rough sketch of what the graph of the sine of x is, and this can kind of give us an idea of what we're finding here. Okay, so go ahead and graph just one period of the sine. There it is. And we're claiming that we have horizontal tangents at pi over 2 and 3 pi over 2. You might have to use your imagination a little bit. It might be the artist's fault that it doesn't quite look like that, but that's what we found there is our horizontal tangents there. Okay, we'll do one example. It's a little bit more challenging. So this time we'll look at f of x is equal to the sine of x plus cosine of x. Same deal. Where does the derivative equal to 0 on 0 to 2 pi? So derivative of sine is cosine, derivative of cosine is minus sine, and we want to set that equal to 0. Well, we'll add sine to both sides, and we're looking at where's the cosine and the sine equal to each other. Well, if you get out your unit circles, that's going to happen at pi over 4. Okay, and the x and y coordinates are root 2 over 2 and root 2 over 2. And it's also going to happen at 5 pi over 4, and where those cosine's negative root 2 over 2 and the sine is negative root 2 over 2. Okay, so those are our x values of pi over 4 and 5 pi over 4, where we have well, we do have horizontal tangents because that's where the first derivative is equal to 0. Graphing this would be a lot more involved. You could do it, make it a table, but you know, we're trying to keep the video fairly short. Okay, so that's a little bit of applications of the derivative of the trig functions sine and cosine. Now we're going to look at an example. Again, this is off my handout here. And so I'm going to read it. I'm not going to write it all down. And it says, we'll make the assumption that the change in velocity over the change in time at a specific point in time of a falling object is given by a second order differential equation, which will essentially be equal to negative 32 feet per second squared, which is your acceleration due to gravity. You can solve that and you get the velocity is equal to negative 32 times t plus your initial velocity. Solving this once more will arrive at the position function. So we'll start you off with the position function. You know, in Calc 2 or differential equations, you could go through and derive. Maybe we could derive this at the end of the semester. So here's your position function: negative 16t squared plus v naught t plus s naught. And v naught stands for your initial velocity, your starting velocity, and s naught is your starting position. And in this case, we're talking about a height. So we'll go ahead and suppose an object is fired straight up from 2 feet with an initial velocity of 80 feet per second. We're going to find the position, the velocity, and acceleration functions. Okay. So the first thing we'll do is for the position, we're going to substitute in 80 for the v naught, that's your initial velocity, and in s naught we'll replace it with a 2. So s of t, your position, is negative 16t squared plus 80t plus 2. Okay. Now velocity is a change in distance over a change in time, so your velocity is going to be the first derivative, so we're going to be using that power rule. So v of t is equal to the first derivative of position, so it'll be negative 16, and we're going to do the power rule, and we're going to bring the 2 down, so that'll make it a negative 32. Subtract 1 from your exponent, so that'll be negative 32t. Plus 80t, and then derivative of the constant of 2 is 0, so we don't include that. Okay, the change in velocity over the change in time is your acceleration, so that's the derivative of velocity, or that's the second derivative of position, and we'll take the derivative and we'll be left with negative 32, and that's your acceleration due to gravity in feet. Okay. The second part asks for determine the average velocity on the interval from 1 to 2 seconds. So we're looking for an average, so we don't need calculus for finding the average velocity here. So we want to find the change in position over the change in time, and that's going to tell us our average speed. Okay, so change in, basically it's the change in distance over the change in time. So average velocity, so from a position at 2 seconds to a position at 1 second, time change was 2 minus 1. I'm going to go on the next page to write out that computation. So you're going to plug in 2 into the position function, and then plug 1 into the position function, and then take the difference. I have not included the denominator because the denominator is 2 minus 1, which is 1, so that doesn't really need to be there. So the average velocity is 32 feet. So we're still going up between 1 and 2 seconds. Problem C asks for the instantaneous velocity. So instantaneous velocity, that's going to be where we use the derivative. That's finding slopes of tangent lines. So we're going to use our velocity equation, which is the derivative of position. So v of t was the derivative of the position function, which is negative 32t plus 80. So v of 1 is 48 feet per second, and v of 2 was 16 feet per second. So this looks pretty good. Oops. Whoops, let's go back. This looks pretty good. So we said our average speed between 1 and 2 seconds was 32 feet per second. So at 1 second, our instantaneous velocity was 48 feet per second, and then at 2 seconds, we've slowed down to 16 feet per second, and 32 feet per second is right in the middle there. So that seems good. We'll do 2 more questions. One question will be find the time required for the object to fall back to the ground, and then what is our velocity as we hit the ground, or an instantaneous velocity. Okay. So part D, they want to know the time required for the object to fall back to the ground. So we're looking at the position, and so that's when the position is equal to 0. So we get negative 16t squared plus 80t plus 2 equals 0, and we get to use the quadratic formula. So it's negative 80 plus or minus 80 squared minus 4 times negative 16 times 2, all over 2 times negative 16. And I'll go ahead and put that in the calculator, and we get t is approximately negative 0.024, and time is equal to 5.025. So we're not doing any time traveling, so we're going to throw out the negative value for time. And so when this object hits the ground, it's just slightly over 5 seconds after it was launched. Okay, so our instantaneous velocity, we'll go ahead and plug in the 5.025 seconds into the velocity equation, and that'll tell us how fast we were going. Okay, and I think it's something like negative 80 feet per second. when we hit the ground there. So going pretty fast. Probably don't want to be underneath the object. Okay, so that was the second part of 2.2.